My name's Casey. I'm an engineer at Tigera, and I primarily work on container and VM networking solutions with a focus really on Kubernetes networking. So I want to talk today about some stuff I've been doing recently to bring self-hosted networking, specifically self-hosted canal for Kubernetes. So start with a definition of self-hosting. So self-hosting is the use of a computer program as part of the tool chain or operating system that produces new versions of that same program. And the kind of classic example of this is a compiler that can compile its own source code and create new versions of itself. Now, in the context of Kubernetes, we're talking about using Kubernetes to manage, update, and kind of redeploy new versions of itself. Now, I want to talk specifically about self-hosted networking. There's a bunch of work and excitement in the community about self-hosting all of the core components of Kubernetes. I think that's a really great direction, but I'm a networking guy, so I'm going to be selfish and talk a little bit about this. So what we're talking about here is running your Kubernetes network using the core Kubernetes components and resources. So in other words, you're using Kubernetes to install the networking that Kubernetes itself will then use. So why would we want to do this? Well, Aaron kind of touched on this a little bit earlier, and it's the same reason that we would want to run anything on top of Kubernetes. Kubernetes is a platform that has been built specifically to make running, deploying, and managing software easier. And your networking is really just software. So all of the advantages and all of the features that Kubernetes provides for running your applications, you can take advantage of by deploying your networking on top of this. If you're already sold on using Kubernetes to deploy your other applications, it makes sense that you want to use it to deploy your networking. So, all kinds of things, install, upgrade, logging, management, authentication, all of this stuff comes for free with Kubernetes. So, if you're not familiar with Canal, it's a project that we've been working on at Tigera with the CoreOS folks to bring together Calico and Flannel under the same roof. So what this gives you, really, is the best of Calico and the best of Flannel together. And specifically what that means is you get a whole bunch of different network connectivity options, both from Calico and from Flannel. And you get powerful security through the network policy engine that Calico provides. So quick step back. The container network interface is an abstraction between orchestrators and networking solutions that's meant to kind of ease that boundary and make networking more pluggable. So Canal uses this, Flannel uses this, Calico uses this, as well as a whole bunch of other networking solutions. And it's really quite a simple interface. It uses network configuration that's defined in JSON, and all you really need to do is implement two commands, either add a container to a network or remove a container from a network. And I mention this because, like I said, Canal, Flannel, and Calico all use this. So Flannel today looks a bit like this. You have a CNI plugin that plugs into your orchestrator. You have an agent that runs on each node. And this agent actually provides that connectivity, that getting traffic from A to B, in one of a number of different ways. So you can have what Flannel calls backends, either a VXLAN or host gateway, and there's a whole bunch of other ones. There's a UDP backend and an AWS backend. And all of these agents running on each of your different nodes are using etcd to coordinate state. And Calico looks from a high level, quite similar, actually. It also has a CNI plugin that integrates with your orchestrator. And it also has an agent that runs on each of your hosts. And this agent provides a couple of things. One, it does this network policy enforcement. And two, it provides some additional backends. The important one in the Canal case is this native backend, which essentially says, you know, hands off Calico, leave networking up to somebody else. And similar to Flannel, it uses etcd to coordinate state. So if you put these together, the current today version of Canal looks a bit like this. You still have Flannel hooking into Kubernetes through the CNI, but the Flannel CNI plugin is actually delegating to Calico so that Calico can get involved and enforce network security policy. Calico is then using its native backend to say, Flannel, you take care of the rest. All the state is still coordinated through etcd, and there's this extra bit in the top right here that I didn't mention before, which is a Kubernetes-specific component, which hooks into Kubernetes and reads policy information and writes that into etcd. So I say this because that's a lot of software. You've got a bunch of different components. We have a daemon on every agent for Flannel. We have a daemon on every node for Calico. We have Flannel and Calico CNI plugins, as well as the network config JSON. We're running etcd. We're running this policy controller. And then we also need to configure all of this stuff. And what self-hosted says is that we want to deploy all of this like this. Way easier. So I have an example of this that I'm going to show you in a moment. Just want to run through how this is actually done using Kubernetes API objects. So like I said, the Flannel, Calico daemons, as well as the CNI config and plugins, all need to be installed on every node in your cluster. And to do this, Kubernetes provides a daemon set as a way to actually run a pod on every node in your cluster. The policy controller is a one per cluster, instance. So we use that. We run that with a replica set to make sure that it's always running. We do general configuration, things like telling Flannel what CIDR to use for the pod network and telling it which backend to use through a Kubernetes job, which lets us do kind of one-shot configuration. And then I have etcd here marked as a work in progress because there's a bunch of different efforts in the community to do self-hosted etcd. And you may or may not actually want to self-host your etcd cluster. Some people will want to keep that as a sort of special snowflake outside of Kubernetes that they can manage on their own. So I have a quick demo of this. So show you quickly. I have just a pretty small cluster here running locally. Didn't want to rely on an internet connection for this demo. So I've got two nodes and a master here. And in the bottom, I'm running just a watch on kubectl get pods, all namespaces, showing everything. You can see there's nothing here. So the first thing I'm going to do is run DNS. So I'm going to create my kube DNS pod. And hopefully that shows up. Well, this would be a shame if this stopped working now. So it is showing up here. So we'll just use that for now. So you can see that the replication controller has been created and the service has been created. I don't have a running pod at the moment. And that's actually, I don't expect to have a running pod because I haven't deployed any networking yet. So I'm going to give you a quick look at this. So I have this canal manifest that deploys all of those components that we were just looking at. I'm just going to do a quick run through because there's a lot here. But I've pulled out all the configuration pieces, all the knobs that you might want to turn, into this config map. So this exposes things like the location of your etcd cluster, the interface that you want to run over, whether or not you want to do outgoing NAT for traffic that's actually leaving your cluster. And it gives you a template to fill in your CNI network config. This manifest is also running etcd on the master, self-hosted. It's a simple single-node etcd cluster, just for simplicity's sake for the demo. And it exposes this through a service with a well-known cluster IP. And that's because we can't actually rely on DNS, because DNS relies on networking in order to start. And then here's the meat of this manifest. We have a daemon set which runs the Flannel, Calico, and CNI containers. So you can see Flannel's running with config pulled from the config map. Same goes for the Calico per node agent, and a container which installs the CNI plugins and CNI config on each node. I have written a job which, quite simply, will write network config to etcd. So it tells Canal to use the 192.168/16 subnet for pod IP addresses, and has configured it to use the Flannel VXLAN backend. And then I have a replica set which deploys the Calico policy controller. So with any luck, this will So, I think something may have gone wrong with my cluster. So I've got, you can see that the daemon sets have been created. The replica set has been created. However, it's not scheduling the pods. So let's just see if there's anything obvious going on here. No events. OK. Sorry? Yes, let's do that. So the suggestion was to take a look at described nodes. So I'm not seeing anything obvious. They're all reporting ready. I will. So my laptop did reboot right before this. But yeah. But it says it has, so kubelet has sufficient disk, sufficient memory, no disk pressure, kubelet ready. That's very sad. So I can, how about I go back to the slides for a little bit. see if I can bring this cluster back up. It's just a Vagrant cluster, and we'll see if we'll continue after that. Cool. So close. So the next part, now that we have Canal installed, I want to talk a little bit about some of the features of Canal, specifically network policy. So we've got some numbers here, which in some contexts might be considered quite good, right? If this was a number of Kubernetes clusters in production, or number of companies using containers. But in fact, they're quite dire. So this is a record of known enterprise breaches in the year 2015. And this is a trend. And really, a large part of this comes from the fact that applications are getting bigger, they're getting more complex, and people are pushing the limits of what traditional network security architectures can accomplish. So as we switch to containers and microservices and more distributed systems, it becomes harder and harder to actually secure those systems. And using a traditional N-tier architecture where you're splitting your application into multiple tiers and sticking firewalls in between each one, what this means is that if an attacker gets into one of your workloads, they pretty much have free reign to attack the rest of your network. So consider a Kubernetes cluster. It looks something like this. You've got N services running, and that's already a lot of connections between, or potential connections between all of these services. And really, the applications we're deploying don't need all of these connections. There's only a tiny fraction of these that are actually useful for the application. The rest here are actually only useful for an attacker. So what we want to do as developers and operators of this cluster is cut out all of these connection paths that we know aren't useful for our application, and actually limit the active connection paths to the ones that are required for the application to function. So a simple example of this, let's say we've got a really simple application. It's a front end. The client accesses the front end, and the front end stores some data in Redis. We stick this on Kubernetes, and we scale it up a little bit. And already we're seeing, this looks a little bit like this. So we've got a bunch of connections here that aren't useful for our application. We want to trim them down. And this is where network policy comes in. Kubernetes exposes a network policy API that allows you to declare this style of network policy directly through Kubernetes, provided your networking solution supports it. So what we've done here is we've cut out all the connections we don't need. We know that our front ends don't need to talk to each other. The client doesn't need to access Redis directly. So we can eliminate all those connection paths. And what we get is something a lot simpler and a lot more secure. It looks like this. So provided this cluster has come back up, which it is still working because it relies on some Docker images. But Tom tells me there is a very similar video online of the demo I was about to give. So I can provide that for you guys. So this looks pretty close. So I'll talk over this. So I've got a Kubernetes cluster here, very similar to the one I was going to show you. This isn't using self-hosted Canal, but the end state is rather similar. So what I'm going to do is I'm going to start by deploying a simple Redis service. So I've got a manifest here, deploys a single Redis instance with the labels demo Redis. So I'm going to go ahead and create that. And I'm also going to expose it through a service. This is all in the demos namespace. We're just using the standard 6379 for Redis. So if I describe the replication controller, you can see that we have one current, one desired, so all is good. So the next thing I'm going to do is deploy a front end that actually uses that Redis service. So this is a simple Flask app written in Python. It serves on TCP port 80, and essentially every time it receives a request, it goes ahead and connects to that Redis, or at least it tries to, using the Kubernetes cluster DNS. And if it successfully connects, it increments this hits bucket in Redis. If it fails, it prints failed to connect to Redis. And then if it's successful, it prints out how many times that this application has been seen and the host that is actually serving this request. So I'm going to create that using a replication controller. I'm going to create 5 of them. And they're going to have identified through a label demo front end. And I'm also going to expose that with a service. So replication controller and service both created. You can see we've got 5 desired, 5 current running replicas of that. So now I'm going to go ahead and I'm going to set up a simple while loop here that's actually SSHing into one of the machines and hitting that service IP. And you can see it's working. So every time it's hit, we see an increment in the number of times that service has been viewed. And you can see that it's printing out a load-balanced collection of pods over here. So this is good. Application's working. The problem is I can access Redis directly as well. So just by running the Redis Alpine Docker container directly through Redis, I can set that hit counter back to 0. You can see here I got to 23 hits, and then it jumped back down to 1. So this is no good because that data is what my application is all about. I need to protect that. I need to not lose that, or else my users are not going to be super happy. So I'm going to create some network policy, and this is actually using the alpha version of network policy. In latest Kubernetes, this is beta, and you can use kubectl to do everything that's being done here. So I'm going to create a policy. Let me just pause this for a second. That selects pods with demo Redis and allows incoming from all pods with demo front end. And it does this to TCP port 6379. I'm going to do the same thing for the front end. So that's going to allow traffic slightly more broadly. It's going to restrict to TCP port 80 because I know that's what my front end serves on. But otherwise, it's going to allow from any source because I want people to be able to access my application. So go ahead and create that. So the next thing you need to do, none of these are going to take effect until you enable isolation on the namespace. And this is what I was talking about just before by setting the default to deny. So if we stick an annotation on the namespace, we'll see traffic is carrying on. Policy is in place. So if I go and try to access Redis directly again, the command doesn't do anything. And that'll just sit there and wait. It's not going to go anywhere. So just to show that this policy is actually working, if I remove the policy that allows the front end to talk to Redis, you can see that we start seeing these failed to connect to Redis messages pop up because the front end can no longer access Redis. It's hitting that default deny behavior. If I delete the next policy that allows traffic to reach the front end, then my while loop over here actually can't hit the front end anymore and will start to time out. And if I remove the annotation on the namespace that enforces isolation, we'll see the traffic starts to flow again. And that's it. So again, sorry about the demo difficulties there. Luckily, we had a backup out there. So here are links to Canal, Calico, and Flannel. They're all open source out there for you to take a look at. If you're interested, of course, Tigera is hiring across the board. I can take some more questions, or you can come chat to me afterwards. Thanks a lot. All right, well, come talk to me afterwards if you have any more questions. Thanks, guys.